Okay, so here we're trying to demonstrate the effect of using emitter degeneration to stabilize the calculation for the collector current. So in a previous experiment, I demonstrated that beta varies unpredictably when the conditions of the circuit change. For example, when the collector current increases, beta is also observed to increase, but it's not predictable. The reason why we add an emitter degenerator is because we want to be able to predict, given some circuit configuration, what kind of collector current will be generated. So here I have the setup. There's a battery which supplies a fixed voltage to the base. In a real circuit for an amplifier, this will be replaced by a bias network. But for the sake of demonstrating emitter degeneration, I've just hooked up a separate battery to the base. And there's a power supply hooked up to the collector. And then there's a resistor tied to ground hooked up to the emitter. And if the theory is correct, then we should be able to predict the emitter current, sorry, the collector current, which will be determined by the voltage drop across this resistor. So the theory is when we fix a supply voltage to the base, there's a predictable 0.7 voltage drop. So therefore, we also fix the voltage at the emitter. And then we know the ground voltage is at 0, so the voltage across the resistor is just base minus 0.7. And then when we divide the resistor on the emitter, that should give us the emitter current. And in a transistor in active mode, the emitter current is roughly equal to the collector current because the base current is much smaller. So we should be able to predict the collector current by just the setup alone. But you can see in this equation that the supply voltage does not actually impact this. And the reason is because whatever the supply voltage is, that voltage will be dropped, that extra voltage will be dropped across the collector emitter junctions of the transistor, dissipated as heat. So I've set up an experiment to using batteries, one or two batteries. So 1.3 is a single battery, 2.6 is a two battery combination to supply the base voltage. And then I'm going to vary the VCC from 5 volts to 4 volts to demonstrate that VCC does not impact the voltage calculations. Does not impact the collector current calculations, sorry. And then varying the resistor of the emitter from 47 to 200 ohms. And then, as you can see in this equation also, beta does not factor in. So the transistor does not actually determine the collector current. All the other components can entirely decide what collector current we get in the amplification. So this is my setup. I've got a voltage supply hooked up to the collector terminal, and then I've got a battery, a single or double. I've shorted this one, so it's a single battery, which is hooked up to the base, and then there's a resistor on the emitter. And by varying these, I've created the actual results. So as you can see, most of these are pretty close. So, but there are some caveats. So this 2.6 volt, 4 volt VCC, 47 ohm emitter resistor has a 40 milliamp measured collector current, which is the predicted one. So these are all within almost exactly the same as the predicted values, but these two are quite different. So this one predicts 12 milliamps, but the actual measured is 20 milliamps. So by feeding 1.3 volts in the base and 47 ohms in the resistor, I'm not getting a 12 milliamp collector current. I'm getting a 20 milliamp collector current, which is very strange. And when I actually use the oscilloscope to figure out what's going on, the base emitter voltage is measured to be 0.4 volts. not 0.7, which is the other cases. But this is very strange because the zero point 0.4 volts means that the transistor is in the cutoff region, or it's not fully turned on. And however, how is it not? It can't be completely cut off because there's still 20 milliamps of current flowing through from the collector to emitter. So I'm not sure why it's showing zero point 0.4 on the base emitter. This is something that I can't quite figure out. And then likewise with this 1.3 base voltage, the predicted is 12.8 milliamps, but I'm measuring 17. And again, BE is 0.4 volts for this one. So we might have another issue that I'm not sure of in my circuit setup, which is producing this. Somehow, this 1.3 volts on the base with a 200 ohm on the emitter is not getting a prediction issue. It's measuring 3 milliamps. But then again, my voltmeter on my oscilloscope, it has an error of plus minus 1 milliamp. So just by plussing or minusing 1 milliamp, you can see there's a 33% error boundary. So it might be measuring wrong, just that the error boundary is much less. However, this error boundary is much higher. This is almost a 50% error boundary. Yeah, that's it for this video.